Hello everyone, and today we are going to have a quick video learning about the Doppler effect. So at this point, we've talked about what waves are, we've talked about sound waves, and we've also briefly just talked about some of those electromagnetic waves as well, but not a whole lot. We've kind of just acknowledged that they existed. We've also talked about our mechanical waves, so longitudinal and transverse, and requiring a medium, and then of course sound waves being that longitudinal wave. So that's kind of a quick little summary of what we've talked about so far. Now, most recently we did talk about sound waves, and Doppler effect is where we're going to be heading next with it. Now, one thing, and we'll show this, the Doppler effect doesn't just apply to sound. It applies to all waves. All right, now we'll look at both of those. How that it can impact those other waves, and how we might use this Doppler effect. Why is this an important thing that waves do or can do? So the first one we're going to look at is the Doppler effect and how sound is impactful, or how it impacts sound. So you can think of the Doppler effect as the rise or fall of pitch due to the motion between you and the sound source. So in general, as the sound approaches, the pitch becomes higher, and as the sound moves away, the pitch grows lower. So here's what this really means, and you've experienced this, and a lot of times it'll be simulated in movies and things like that as well. You think of a car, and that's what I have in the upper right, that animated GIF there going on. If we have a car traveling, and they honk your horn as they pass you, you'll hear this kind of like high pitch, and then it'll shift to a low pitch as it passes you. You kind of get this kind of, right? It kind of does this like high, low type of sound. And that's not just the normal noise of a car. What's happening, and as you can see in this animation above, is we have our car traveling. Now once reset, so we have this car traveling. You can see these waves being pushed out from it. They're actually getting closer and closer together. And so there's this person that's standing here. You can see that as that car is passing, we have a compression of these waves. They're closer. Now, if they're closer, that's going to increase the overall frequency. So effectively, the Doppler effect changes the frequency of the wave, and it can change the wavelength, which we'll look at in just a second. So kind of looking at those things, which can cause a shift in what's happening with the wave, because you can see now these waves are getting, once it resets again, are getting closer and closer. They're closer together, which means their wavelength, more specifically, I kind of misspoke when I said frequency earlier, their wavelength is getting shorter. All right, and in part that's because they're gaining a little bit of extra velocity because of the car's motion. The motion's important. If the car wasn't moving, there wouldn't be any change. The other thing to include then is afterwards you'll see them having a much bigger spacing between, and what's actually happening here is that's where you'll see it go from this high to low, because now we have a greater spacing occurring at the back end. All right, so now there's like this compression up front, and then there's a gap in the back, which causes it to sound a little bit lower. All right, so that's kind of a quick little summary of that. Let's look how it affects our next, and that's going to be our light. So we got our images here. I'll kind of move myself a little bit out of the way here, and then so with these images, I'll explain them in just a second once I explain what it is. So the Doppler effect with light can also cause changes in light, and we refer to this as something called the red shift or the blue shift. And what this is deliberately saying is things are either becoming more red colored or more blue colored. It's an actual shift in the coloring of the object. And so there's really a couple of ways we can look at that. If something is shifting towards the blue, that means it is actually moving towards us. And if something is shifting towards the red, it's moving away from us. And this is something that's very, is used a lot in astronomy. And that's actually some of the evidence we have as to how we know if things are moving away from us or towards us in space. And actually what it turns out is just about every single object that we can see is redshifted, which means that just about every object is moving away from us in space. And that's where they use this as some evidence for like the Big Bang Theory and things like that, in which there's a center explosion or kind of force that's now pushing everything away from it, because we're saying, well, everything's moving away from us, which seems to indicate there's some central point that things are moving away from. Now, what these images are showing. So in the upper right hand corner, so if we look at that one first, this top one is like a normal, what it would normally look like. There's no change. So we have like our standard wave. That's what we can compare it to. Like if there's no motion, here's what it would look like as an example, okay? If this, and this is a representation of a galaxy, maybe we could see with astronomy tools, we could have, now you can see that these wavelengths are getting longer, and that's representing that this object is now moving away from us. You could almost think of it as it's being stretched. Okay, that information at its normal, as you see above, is kind of getting pulled. And if you think just like if you were to grab each end of these almost like a string and sort of pull it a little bit, it would actually stretch out. And then the next one is where it's moving towards us, and so now it's getting compressed. And so now we're getting this pushing together, and that's what's happening with this shift. And you can see this little black line. So this is where it's like normally, and then there's this black line. And we can see that the red is on the far right, blue is on the far left. This red line is now slightly to the right, which is our red shift. And then this one's slightly to the left, which is our blue shift. The color is actually changing, and that's what I wanted to show this bottom image. Our red have a longer wavelength. When you see something that's red, it is a wavelength that's generally between 600 to 700 nanometers. That's wavelength. That's probably closer to 650. If you're in the 600s, it's more yellow orange. But that's how we perceive that. That's how our eyes work. Now, if we have something that's more blue, we're now shifting towards shorter wavelengths. We're now looking in that 500 nanometer range. For it. So what that tells us, when you have these things shifting back and forth, they actually do change color. It's very, very slight, but we have tools that can recognize this change in wavelength, and that's what we call redshift, blue shift. It's almost like it gets a more blue tint or a red tint. You can kind of think of it as almost like a photo filter. It's just generated by the movement of that object. All right. So that's your introduction to the Doppler effect. Now we're going to do a few things. I'm going to have some videos linked in this video. You'll see them either in the description or they'll pop up on the side for you. And then there's also going to be a few other things we'll work on with it as we expand our understanding of the Doppler effect. If you have questions, absolutely let me know. Have a great day.